Андрей Анатольевич, в частности, приветствую.
Да, Александр Маратович, в частности, вас. Hello, everybody. Summer ended and we have to start our work. And despite of summer weather now, now we have first talk in this semester of Katerina Glinyanaya, devoted to the functional limit theorem for point processes related to Arratia flow. Katya, do not expect that at the first talk at this semester we will work hard. So we just expect from you that you will work hard. We just participate. Okay? Okay, let's go.
I consider Arratia flow. So I just recall that this is a family of Brownian martingales. So this is the Arratia flow.
I'm sorry, can you see?
Katya, you start the demonstration of your screen.
Yes, it was my question also.
I didn't start?
Yes.
You stopped.
Oh, just a second. Just a second, I can see how. Okay, now you can see my screen.
Yes.
Oh, okay. So I consider the Arratia flow. So this is this means that we have for any point u, x from u is Brownian martingale, which start from point u. To u, and for each points u, we have order between any two trajectory. So we have less than x from vt if u less or equal than v for any t greater than 0. And the joint behavior is such that they move independently up to meeting and then occurless. So we can write it in terms of its joint quadratic variation t, so it is equal to the integral from 0 to t, indicates that x from u s equal to x from ds ds. So in my talk I will consider the point process that which associated to the Arratia flow in the following sense. It is known that, so we know such fact that for any bounded Borel set, so okay, I will consider interval for example, for any interval 0 n, for example, the image of this interval for any positive time t is finite. So we can denote by, so this is a finite number of points. and also the number, I will denote the number of points. The number of points of whole line at time t that came to some set delta is also finite for delta with finite Lebesgue measure is finite if we have. So I will denote by NT is the point process that counts that this number, this points. This is just number of points that came from set delta. And I will consider such a point process, and I just want to say something what is known about such a point process. So in the paper by
Katerina, maybe you don't have to speak in general about this point process because there are a lot of publications devoted to it.
no,
but maybe you have to point your aim, what you will prove, and after this maybe we can discuss related literature. Yeah.
okay, so okay, of course. So so in previous my work with Fomichov, we proved such a theorem. So that this was done. That we have the central limit theorem in the following sense: minus its expectation 0n by square root of n weakly converges to Gaussian random variable with known variance sigma t, which is equal just constant that depends on time t in such a way. So and now I will generalize this limit theorem. So I want to consider the integral with respect to this point process. So first we will define with respect to nt. So this is, for example, from 0 to 1, f from u, and t from d. And for such integrals, I will prove the limit theorem of the following form. Theorem. So the integral from under some conditions that I will specify later, we will consider du minus its expectation t 1 over n converges weakly again for Gaussian random variable, and moreover we have proved that we have convergence not only for a fixed time t, but in Skorohod space. So this is my aim, and what I need to prove it. So first, what we know about such point process. Yeah. NT. So in the paper by
Katya, I have a question. Doesn't sigma depend on f, the right hand side?
yes, of course we have here. I should write.
And do you know the dependence?
Yes, for fixed time t, I have exact formula for this sigma squares that depends on f. Yes.
Thank you.
So in paper by Mansin, Rajesh, and Tribe, Zaboronsky, they proved the existence of n-point density of NP. I will denote it by rho and index at t. This means that we can write for example, for points v1. The probability that exists points in dy1, dyn. It's informal definition, but it is some. So it's some sense we have this endpoint such density, and that I will also use the upper bound for such density of the form. So for any n, it is less or equal than pt to the power minus n over 2. So this is for all 2. Later in 2011, Tribe and Zaboronsky, they write this density in terms of Pfaffian. So it is so they obtain exact formula, but in terms of Pfaffian of matrix. But I will not use it in my talk. except of, so I have the first row T, which is equal 1 over square root T. And the second, I will use the property of the second of 2-point density U1, U2. It is a quite big formula, but I don't know, T 1 plus U2 minus U1 over T minus B squared over 4TB and minus I will use it in my proof. So I I will need a rate of convergence for such function for different points U1 and U2. So we know about this point process a lot, and now I would like to talk about what was done for what limit theorems was obtained by another mathematical introduction for different point processes. So first that I would like to say that in the work by Karhin he proved the central limit theorem for number of points. So in my notation it's 0 and that I proved that I say we have it, but not for only my point process, but for general Pfaffian point process, but it have such condition for endpoint densities that is not easy to verify. So we proved our theorem without this result. Also, a big work was done for determinantal point process. This is such point processes for which it endpoint densities is determinant of some matrix. Not matrix of form, for example, K of
So we can say that, for example, Arratia flow is Arratia point pros is not determinant. Pros,
Yes, yes, it is not. It is a Pfaffian point process.
Is the example of the determinant point pros? Do you know?
Oh. I am not ready to say it now.
For example, as I think Poissonian pros, point pros is
Yes.
Pfaffian and determinant. Yeah.
Yes, yes, it's so, but it is maybe it's not
Which are
interesting.
obtained like compound Poissonian pros, maybe something like this. Yeah.
Yes, I think.
Okay.
So for
and
such, yes,
he proved this central limit theorem for such processes. Yeah.
yes, and not only for number of points, but for such functional like of this type. So if we will 1 xp, where xi belongs to this point process x, I will denote it. So he proved also the limit theorem for such functionals. So it is also in some sense that we can consider it as integral of f from
Gaussian integrals. Yeah?
yes, our integrals p and t.
Yes, and this is like U statistics, and the
Yes.
limit is some multiple Gaussian integral. Yeah.
Here, yes. And also almost the same was done not for determinantal point processes, but so-called negative or positive positive associated. This means that for negative associated, for example, for subsets AI and BI borrow set such that union of A's do not intersect. Union of B is equal to 0, and for negative associated, they need this inequality x a k b1 x from bn less or equal to product of x from a1 so on x of ak multiplied by but also this was hard to me to prove and I don't know if it is true for point process associated to Arratia flow if it is in some sense negative, in this sense negative or positive associated. So but in work for by Buenas and Cavantier, they proved also the central limit theorem for also for U statistics of such point process. So maybe I will go now to my result. So first we need to precisely define integral from 0 to 1 from f from x and t dx. I will denote as a t of f. It is a continuous mapping from L to 0, 1 to L2. And so this is continuous. And with variance of AT of F, I will need it later. So it is equal to integral from 0 to 1, f from u1, f from u2. Here, the second of the 2-point density of u1, u2 minus rho t to the first to the square. First to the square from u1, u2, du1, dut, u2, and plus 1 over pt, 1 f square from u1. Here the density, so I do not write it here, u1. So we can see that we have such a good formula for variance, and also if f belongs to L pair from 0, 1, then also the moment, the path moment of f is finite, and it is we can get exact formula in terms of the thrust, but I will not use it today, so I will not write it in a precise way. But we know
Katya,
that, yes.
Katya, I have a question. As I understand, rho 2 is 2-point density, right? Rho 1, 1-point density. But what is rho 1 of 2 arguments?
Oh, this is my mistake. Oh.
Thank you.
U1, rho t, U2. Yes. This is one. Yes, you're right. So I will not prove the this if you don't mind, because it's just computational. So, or if you want, we can discuss it.
No, let's go for it.
Okay, so now to the limit theorems that for so the first one for fixed time t, greater than 0, I will my statement is that for and function f let it be periodic on R with period 1, such that F has certain moments, so it 3 from 0, 1 is finite. Then we have that integral from 0 to n f from x and dx minus its expectation x and t dx converges quickly 1 over n to Gaussian random variable, as I said, and this sigma t square of f is equal to, so we have almost the same for that we had for variance, but not the same. So we have here f from u1, f from u2, and here I will write here. I just will write here, but u2 plus series to series. u1 minus u2 plus L from 1 to infinity.
Ekaterina, how natural is the assumption that F periodic in this area? Is it natural or not? Because you exclude a lot of interesting functions. While assuming that F periodic.
Here, just a second, I will finish my formula and then we will discuss about periodicity. And for issue of u1 minus u2 is this is just u1 u2 minus 1 t u2. So this function depends only on difference. So I write in such way. So now about periodicity of function f. Here in my proof I used it, but maybe we can somehow make more a less restrictive assumption on f, but
No, my question is a little bit different. Is it a natural assumption in this area or not? Maybe assuming that F is periodic, you can get some interesting examples of particular processes or something like that, which are really useful in this area. I'm not well familiar with this Arratia flaws. I don't know.
In the work that I mentioned above, in this case, they also considered periodic functions for.
Yes, I think that is very natural because point process related to Arratia flow is stationary. This is the first reason. The next is that it has, as you will see, good mixing property. So more or less, when you have periodic function, you have a sum of independent random variables which are equidistributed. Of course, we can weaken this assumption and consider some almost periodic function or something like this. But of course, we cannot expect the same behavior from for the general function. For example, if it goes to 0 and infinity, the behavior can be very different. Yeah? So this is natural because of stationarity of the point proofs.
Okay, I see. Thanks.
Okay.
Yes, maybe. So the proof of this statement, so we will write this integral as sum of integrals from 0 over k to k plus 1. And this now, due to periodicity, as we just discussed, these random variables, I will denote them by k. So they are they have distributed this random variables, and also what we need to prove the central limit theorem for sum of random variables with identical distribution. We need to know that they are weakly dependent, and for this I use so-called alpha mixing coefficient for the sequence yk. Do I need to recall the definition, or I just can say that we know the upper bound for this coefficient for Arratia flow? So for Arratia flow, we know that it has a good upper bound, some constant, and here integral from h to infinity x squared dx.
So this inequality was proved by you, yeah?
Yes. I proved it in my previous work. So, and using this estimation on alpha mixing coefficient, then I will use the central limit theorem for weakly dependent random variables, and here also I need the third moment of yk, so I need to have that yk have the third moment. Alpha mixing coefficient for them is
this is Tikhomirov theorem, yeah?
Yes. So CLT by Tikhomirov. This will equal then some constants A minus EH. And under these conditions, we have that sum of yk minus its expectation 1 over weakly convergence to 0 square. But and also one of the problem is to prove that this sigma square that is not 0, so sigma square is 1 over n variance of sum. And in my case, I prove that it has such a representation in terms of function f and density of point process. So we can see that we can calculate it precisely. Now the next step is to prove that we have central limit theorem for points T1, T2, and so on, Tm. Now the vector of 1 over n, and here T1 du minus its expectation T2. So such a vector also converges to Gaussian vector. Convergence to n0 here some sigma that depends T1 and so on Tm and from function f. But I do not have precise formula for non-diagonal elements of this matrix sigma, but again for diagonals it is known by previous result.
Katya, let me ask you, you don't have this precise formula of non-diagonal elements of the matrix sigma only for us because it is very complicated, or you cannot imagine how to get this non-diagonal elements?
So we can write, so if I denote them by Ci, it is such some second I1 to m oh no sorry, so I didn't write it. So we have 1 over n just covariance of this integrals
I
in
understand.
different point.
You don't write this expression.
Yes,
just,
but
gives us the flavor.
yes, but the problem is that I don't know even exact formula for covariance, so it can be right maybe in T from T. But to get this formula, I need to know, for example, for integral of such kind, but I didn't obtain exact formula because we have here different time point for point process NT, and
I see. So you
I don't
need
know, yes.
some
I don't know how
limit
to.
statement for the double sum, yes?
Yes, yes.
Katya, you also don't know what the covariance is for the case when f is equal to 1? In this
So
simple
just,
case, which...
no, so just for some one, maybe the precise formula, no, I do not have, but maybe I was trying to obtain some estimations, but not a precise formula for different time t for number of points. So I do not know it.
Okay,
Yes,
thank you.
So the
But
question about the different time.
I'm sorry, I didn't hear well.
Okay, the question is only about different times, yeah?
Yes, yes. So it's about different times.
Okay.
So this limit theorem is not hard to obtain from the 1 point time t, and now to obtain the limit theorem in space, in Skorokhod space with respect to time t. So what do I mean? So if I consider as a process x, I will note here, and f from t, it is just 1 f from u to u minus its expectation and to u. So I want to prove that this process f as process with respect to t weakly converges to some Gaussian process psi in Skorokhod space.
Is it obvious that the path of the integral belongs to D?
So we can, it is not obvious, but for the first, if we consider NT from some set delta as function from T from
So it can be proved.
0 to,
right?
yes, from 0 to some T capital, it is a step function, and we can choose Godlach modification, and we will consider such modification of NT that so and integral will have also Godlach modification.
And you consider Skorokhod space with point 0 excluded, right?
Yes, here without
zero. I see, thanks.
Or maybe it is better to write maybe from T0 to T. So I need to step from 0 later. So to obtain a weak limit in Skorokhod space, we need to verify density of this sequence, and one of the conditions that we can verify and will guarantee the big convergence is following, that if we will consider times t1, t2, then expectation of x and f from t minus x and f from t1 to some power gamma x and f from t2 minus and f from t, if it is less or equal than t2 minus t1 to some power alpha, then the weak convergence in space D will follows from the finite dimensional convergence intent. So now I will check that we have such estimation, and this is for all n. To do this, again, I will write xn as sum of
yes. Katya, what is the assumption on alpha and gamma here?
Alpha is greater than 0.
No, alpha is greater than 1.
Yeah, greater than 1 and
it is for more of condition.
I will check in ATM first.
No, for sure it's larger than 1.
No, it's greater than.
It's strange. For example, take Bostonian process. Yeah. So it is not Kolmogorov condition.
No, it's Billingsley condition.
For
yes, and here they have 0.
No. Alpha is larger than 1. It's for sure. Otherwise, it doesn't work.
No, I found in a Curse book, page 139, and here is the condition Katya wrote. Here is written beta divided by 2, but beta is positive just. And theta.
Yes,
it is the last. And I mean, yes.
Yes,
and alpha has to be larger than 1. Mm-hmm.
And here gamma is
larger than 0.
Greater than 0, yes. Yes. Okay, so here I will consider. Sorry. This is, I will consider the first T2 minus F from T. I will write the sum, this axis as sum of from 0 to n minus 1, and here I will write as integrals from k to k plus 1 f from u and t du minus integral k plus 1 f from u and t1 du, and I will just write here two sums, n minus 1 and 2 here. And the same from j plus 1 to u minus f from u and t du. And now again there I will use stationarity of with respect to k. So this is equal to okay, I will write here L from u to n minus 1 station. And here just from 0 to 1 u minus 0 1 f from u to 1 to u. And here integrals from L plus 1 and t2 tu minus 1 du, and I need to multiply by n minus L here. Oh, I'm sorry, for x's I have here 1 over n. 1 over n. So here again for large n, I will use alpha mixing coefficient, and so we can see that this is equal just this sum from n minus 1 of this two modulus and minus 1 over n L this modulus. So for here expectation, and this series convergent, so it for all n it is finite with respect to n, and to obtain the estimation with respect to difference t2 minus t1, I start from the first summand. So let us consider square. So for the n equal to 1, we need to estimate t1 du and here the same, but another times t2 du minus integral f from u and t1 du. So I will just estimate it using this inequality. So this is just to the product of expectation of squares, and let us consider one such difference and t1 du to the square. So we can write it in the following sense. So first, this integral, now we have t1 less than t. We can rewrite this integral in terms of previous time. I will show on the picture. So we have t1 and here time t. We can obtain the Arratia flow from this. So we have here some points, and the points on the time t is obtained. I will write here by function p with index at t1 t from. So we have such Brownian web that transform points at time t1 to time t. So we can write this integral as integral from t1 t from u and t from u, and here plus maybe I will write that in such way, f from u I. So we just need to add points u I u from x r t from 0 yes, from 0 but x, but not in t1, but phi at t1 t from u belongs to 0 1. So we just need to add some points. So first for this, so writing this integral, I will consider the first part now and then estimate another. So this one is du to the square. This is just estimation 0 1 0 1, and here f from t1 t at point u minus f from u, and t, oh I'm sorry, here in t1 and t1 du. So now I will use that mapping phi does not depend on nt at time t1, so we can write it in just this is integral expectation yes. I'm sorry, I am in hurry, but here in such. So this is the expectation. I can write just here method phi t1 t from u minus phi from u phi from t1 t from b minus phi from u, and here I will write upper bound because we can estimate the endpoint density or 2-point density of process n just with some constant and du dv. And now for this functions for this expectation, we can obtain the upper bound that depends only on difference t minus t1. So for this expectation, I will not, I have no time to write that. Let me denote it by h from uv and t1. So h from uv t1. Sorry, we have an estimation here. I'm sorry. T1 minus T is a constant. So and here again the same we can do for this expectation and we will obtain that this inequality holds. I'm sorry. This inequality holds with gamma equal to 1. So we have weak convergence in Skaraholt space for such integrals.
But what is alpha?
Alpha here. So I had the estimation that upper bound of some constant t minus t1 multiplied by t2 minus t, and it is less or equal than t2 minus t1 or
Constant n square, yeah?
to the square, yes. So yes, so we have such estimation.
Okay, so we have functional central limit theorem now, yeah?
Oh yes, I think we have, yes.
Okay. So this is all results which you want to present today?
Yes, today is so.
Okay, so maybe somebody have questions or
Yes.
some comments. Okay, please.
So you know that your sequence YK is strongly mixing, and therefore you need the third moment for your central limit theorem. Now I'm only talking about one-dimensional central limit theorem. But it's known that whenever your sequence, stationary sequence, satisfies a stronger mixing condition, for instance, uniformly strong mixing, then, for instance, 2 plus delta moment is enough. You don't need to assume that the third moment is finite, so it suffices to assume that just 2 plus something moment is finite. My question is, have you ever checked that your sequence satisfies uniformly strong mixing or some stronger regime of mixing? For instance, uniform strong mixing. Whenever you get it, so you can prove your theorem under weaker assumptions.
Yes, so I will not have here this third moment, yes? But...
Yes, 2 plus delta moment.
Okay.
So you never checked whether there is a stronger kind of mixing.
Okay, thank you. I will
No,
check.
it's a question.
No, I didn't check it.
But as far as I remember, in Tikhomirov theorem, it is it necessary to have third moment or just 2 plus delta also?
No, I think that with strong mixing, it's not enough 2 plus delta moment.
I just tried to recall this Tikhomirov theorem. Katerina, do you remember it?
Oh, I think for such alpha mix coefficient, for such upper bound for alpha mixing coefficient, I don't remember, but maybe also we need only 2 plus delta, but
because we have a very good decreasing speed of this alpha mix coefficient. Yeah, it depends not only on the kind of the mixing, but also on the speed of the mixing. We did not think about other mixing coefficients, maybe because we don't have such an aim just to establish as weak as we can moment conditions. Our aim just to study Gaussianity, which is covered inside of the Arratia flow, because we know that the flow of sigma fields related to Arratia flow is very complicated and is far away from the usual Gaussian filtration. But this limiting processes, I think that Katerina will present to us this semester next talk about the multiple integral processes. Then this limiting process look like a Gaussian generated by Gaussian field. So it was our aim. Of course, maybe under other mixing coefficients we can get more weaker moments, but it was not our aim. Yeah.
Okay, I see. Thanks.
I would also have a question, if I may.
Yes.
So I have two questions, in fact. So one question is, you start the Arratia flow from really a continuum from every point in the real line. Does it make a difference if you started from every point in the integer lattice? So you just have a locally finite initial configuration. Do you think that the results will change, or do you expect exactly the same results as you had before?
So you just said it. So if we start from integer points.
Integer point. Will the results be the same effectively?
Maybe we can expect the limit to Gaussian process, but we do not have such. Sorry, we do not have exactly to the formulas for this endpoint densities. So maybe we will have another.
Okay, but is it not? I mean, I would suspect that it's easier to have an explicit formula for the endpoint density in this case, in the case when you start from integer, because then you would expect just some combinatorial argument to give you.
Yes, Max, but this formula can be rather complicated. I think you can get it, but you will see rather complicated formulas. I think that Nikolai Vovchansky will present to us something like this formula which you want 2 weeks later, and we will see that it is not very very nice formula. Yeah.
I see. And the second question is kind of related, but only a little bit. So it appears to me, of course, that the point process that is induced from the Arratia flow, it is a Markovian process, right? Isn't it? So it has no memory.
With respect to
time, with respect to time, isn't it the Markovian process?
Absolutely. With respect to time.
Yeah. So the time evolution of this point process is a Markovian dynamics. So
yes.
do we know the generator of this as a generator on the set of point processes? And is it anyhow possible to make any conclusion from that if you talk about the time evolution of these quantities?
I don't know for now. We didn't study it. It's
you see also this is a good question, but it is Markovian if we consider it on the all real line. For example, if you consider this nt from delta, fixed delta, it is already not only non-Markovian, it is some kind of complicated functional from this Markovian process. So to get the functional limit theorem, we thought about this, and you can see the flavor of this Markovian structure in the last estimation, where we use this phi. Yeah, this is exactly what you wanted. Yeah,
yeah, I see.
This is Markovian structure where we use it. Okay. Other questions, please?
I also have a question. I'm not sure whether my question is good and makes sense. I would like to consider the problem from another perspective. You started with a random measure, and of course I would like to see the similar result, but in terms of measures. You can consider, so you write the integral from 0 to n, but later you write this as sum, where the measures was defined, where you integrate with respect to measures which are defined on every integral. But now can I consider the random measure? I mean, the first measure, it is just a measure n of t minus its expectation. Then the second measure is on the another interval, and so on, and write the central limit theorem, but for measures. Whether it makes sense and whether we should expect to have some limit at the end.
Such measures, yes.
Right, and then you write the sum, but you take you can put the index k, where k it is a measure which is defined only the interval from k minus 1 to k.
Okay, Vitaly, actually it is our aim, but we can reformulate it, because when you consider central limit theorem, you always have to subtract something, yes, to get Gaussian limit, to get to apply the central limit theorem. So we can speak not in the terms of measures, but in terms of functionals on the functional space. And actually, it was my proposition to Katerina, and we consider multiple integrals in such a way that we have a Gaussian field in the limit. So we start from these point processes. One can organize this random functional A, which was presented in the beginning of the seminar. And now we say that the set of such functionals converge to some Gaussian field. And moreover, we can consider we can consider integrals, multiple integrals with such compensated measures, and get the multiple integrals from those fields, but in very special manner. Katerina will present it in the next talk during this semester. So we already did this. Yeah. Okay. Some other questions, please.
Okay, then probably very short question. It is not exactly the result, but you showed, you talked about the 1-point density, and where, of course, for 1-point density, it is trivial that it has to be constant because the process is has the same distribution with respect to shift. But probably you have very simple explanation or some reason why the constant 1 over square root pi t.
Because
You work with that a lot.
Yes, this is just expectation, because you can use 1-point density and law of large numbers. And then you will get the expectation of the number of points at the 0, 1.
Okay, okay,
Yeah.
I got it.
Yeah.
Okay, thank you.
Okay, other questions, please? Okay, if there are no questions, then we have to thank Katerina for the first talk in this semester. Katerina, thank you. And then next talk will be by Vitaly Konarovsky after a week. So thank everybody, and bye.
Bye.
Bye bye.
Bye.
Yeah.
Bye. Thank you. Bye.